Hello everyone, my name is Lu and I'm a PhD student at University of Pennsylvania. In this video, I'm going to tell you about minimal cycle representatives from persistent homology.
Persistent homology is one of the main tools in topological data analysis, which uncovers the shape of data. Given a discrete set of data points, we approximate the topological space underlying the data by constructing a simplicial complex. This construction expresses the structure as a union of vertices, edges, triangles, tetrahedrons, and higher dimensional analogs. As we can see, this dataset has the shape of a torus, but real-world data usually lives in high dimensions and have very complex structure that we cannot directly visualize. Topological features have proven effective when characterizing complex data, as they're qualitative, independent of choice of coordinates, and robust to some choices of metrics and moderate quantities of noise. First, we will see some examples of cycle representatives, also known as generators. An important challenge with cycle representatives is that they are often not unique. I'll then introduce a reasonable solution to the challenge, minimal cycle representatives, and 4 algorithms for finding them via linear programming. Let's begin with cycle representatives, or generators. Cycle representatives of persistent homology class can be used to provide descriptions of topological features in data. For example, this point cloud lives in a plane and has a 3-loop structure. The colorful loop on the lower right is a cycle representative for the loop it encloses, which is a one-dimensional topological feature. However, cycle representatives are not uniquely defined, and the non-uniqueness creates ambiguity and can lead to many different interpretations of the same set of classes. As you can see, the original cycle representative is jagged and does not provide the most concise geometric description of the whole. One approach to solving this problem is to optimize the choice of representative against some measure that is meaningful in the context of the data. For example, this colorful loop is an optimized version of the original cycle representative. As we can see, it is much smoother and geometrically concise. Before getting into the specific algorithms for finding minimal cycle representatives, let's go through an example filtration. Suppose we have a point cloud consisting of 6 data points living in the plane. Each point is called a zero simplex. Then we grow a ball of radius epsilon around each data point. When 2 balls pairwise intersect, we connect the centers of the 2 balls with an edge, which is also called a 1 simplex. When 3 balls pairwise intersect, we connect the centers of the 3 balls with edges and then fill it in to get a filled-in triangle, which is also called a 2 simplex. In general, we connect k points and get a k-1 simplex whenever k balls pairwise intersect. At this filtration step, we add in edge dE and we get a cycle, as indicated by this orange loop. The edge dE is called the edge born at the birth time of the cycle. The edge dE is called the edge born at the birth time of the cycle. We then continue with the filtration and add in more simplices. At this filtration value, we add in edge CF, and then also triangles CFG and CEF. Now as we can see, the cycle we had before is completely filled in, or now becomes the boundary of a chain of some triangles. Thus, we say triangle CFG is the triangle born at the death time of the cycle. Note that there could be multiple triangles born at a single filtration value, but we impose an order on them so that we have a simplex-wise filtration. The simplices are first ordered by their dimension and then by their filtration value, or the radius of the balls, epsilon. And lastly, we arbitrarily break ties by alphabetical order. Having defined what we mean by the birth edge and death triangle, now we're ready to talk about minimal cycle representatives. The general problem can be formulated as below. Imagine that we have an original cycle representative XRH, and we want to optimize it. We want to minimize the original cycle representative with respect to some loss function, which measures the size of the generator, while under the constraint that the minimal cycle representative should have the same birth and death time as the original cycle. A natural question then is, how do we define the size of a generator? The first approach is to define it as the number of edges in the generator. This formulation was proposed by Hiloka et al. In 2016. We could assign each edge a uniform weight of 1, and then take the zero norm, which is just the number of non-zero elements in a vector. Then we're minimizing the number of edges in the generator. The constraint is that the solution, which is the minimal cycle representative, must be a linear combination of the original cycle and some previous boundaries and some cycles born and die before the original cycle. This basically ensures that the optimal cycle representative we obtain has the same birth and death time as the original cycle representative. For example, suppose we have the original cycle as shown here. The original cycle representative can be expressed as a vector, which is a linear combination of the edges. Or one simplest. The L0 norm of the original cycle representative is 7 because it has 7 edges, or because there are 7 non-zero entries in the vector. If we add to the original cycle the boundary of triangle ABC, which are the 3 edges AB, BC, and CA, we get the following vector, which corresponds to the cycle representative shown on the left. The resulting cycle representative has an L0 norm of 6. A similar variant of the first approach is to define the size of a generator as the total length of edges in the generator. The only difference here is that we define WLAN as the weight matrix, whose ith diagonal entry is equal to the length of the ith edge. We modify the loss function as the one norm of the product between WLAN and the optimal cycle, which can be understood as the total length of the edges in the cycle, and we keep the same constraints as before. As we can see, the optimized cycle representative has a shorter total length than the original cycle representative. Formally, we call the previous two approaches of defining the size of generators as edge loss methods. We refer to them as uniform-weighted and length-weighted edge loss methods, respectively. Next, we will see some triangle loss methods. Approach number 3, total number of triangles the generator bounds. We use V to represent a linear combination of triangles, and the optimal cycle will be the boundary of those triangles. The solution vector V will be called the optimal volume. Similar to the edge loss methods, we can assign a uniform weight of 1 to each triangle and minimize the L0 norm of the vector V. The constraints in the triangle loss optimization problem ensure that the optimal cycle we obtain captures the same birth and death information as the original cycle. The optimal volume must include the edge born at the death time of the cycle, denoted as sigma death, and some triangles born during the lifetime of the original cycle. In addition, the optimal cycle, which is the boundary of the optimal volume, must contain the edge born at birth time and no edge born after. Again, let's see an example with the previous filtration. First, we must include the death triangle CFG. However, now the boundary contains edges born after the birth edge, but not the edge born at birth time. So, we will need to add in more triangles to satisfy those constraints. Then we add in triangle CEF, but the constraint's still unsatisfied because we add in triangles ACG. So we add in triangle BCD, and now we get an optimal volume with a boundary that satisfies the constraints of the optimization problem. The edge loss optimal solutions could be different from the triangle loss optimal solutions. As we can see, the edge loss solution bounds 6 triangles, while the triangle loss solution bounds 5. Lastly, we have another triangle loss method, which defines the size of a generator as the total area of the triangles that the generator bounds. We define a weight matrix W area whose ith entry is the area of the ith triangle, and the loss is the L1 norm of the product of W area and V, which gives us the total area of the triangles the generator bounds. The constraints remain the same. Here is an example where the four algorithms give us different solutions. The point cloud is randomly drawn from a normal distribution. As we can see, the uniform weighted edge loss solution has the fewest number of edges. The length weighted edge loss solution has the shortest total length, and the uniform weighted triangle loss solution has the fewest number of triangles, and the area weighted triangle loss solution has the smallest total area. Thus, we see the four algorithms do minimize what they set out to minimize. Thank you for watching.